In this problem, we have a spherical balloon that we're trying to inflate. As we inflate it, the volume increases at a rate of 15 inches cubed per minute. What is the rate of change in the radius when the radius is 10 inches? So the radius is currently 10 inches. We know that the volume of the balloon is increasing, which means the radius must also be increasing, but we want to know by how much in order for that volume to be increasing. So we want to remember the equation that relates volume to radius for a sphere. Probably not one that you know right off the top of your head. Maybe you remember it. I definitely think area equals pi r squared is a little bit easier for a circle, but with a radius, the volume, relating a radius for a spherical balloon is 4/3 pi r cubed. Volume is 4/3 pi r cubed. And now we're going to end up taking the derivative of that with respect to time. So taking the derivative, we have the derivative of 1v is just 1 dv dt. You can write that 1 or not. It doesn't change anything with multiplication. On the other side, a little bit more interesting, I can bring down the power, subtract 1 for the new power. Well, this is a lot to combine, so I might do it in 2 steps. You can also just use a calculator. I'm just going to leave that 4/3 pi and just take the derivative of r cubed to be 3r squared. That makes it a little bit easier to see that these 3's cancel. Or use your calculator, 4/3 times 3 is 4. So the derivative of volume with respect to time is just 4 pi r squared when you multiply those constants together. And what else do we need on here? Well, we took the derivative of r, so we would need a dr dt as part of our derivative. The derivative of the radius with respect to time. And now we can figure out what we are given and what we're asked to find. So based on this original equation, our two variables are v and r, right? Pi is a number, so that's not a variable. But we have v and we have r, and then we have their respective derivatives. So we have dv dt as well as dr dt. I want to look at the numbers we're given and also the units we're given. First number says the volume increases, so we're going to have a positive derivative at a rate of 15 inches cubed per minute. So first of all, it says volume. So we're picking between v and dv dt, and the reason we know it's a derivative is because it increases at a rate, it has 2 units, it has a lot of indications that tell us it's a rate of change, it must be the derivative. So dv dt is a positive 15 inches cubed per minute. So my measurement is in inches and my time is in minutes, and that's in cubic inches per minute for the volume then. And it says, what is the rate of change in the radius? And right now the radius is currently 10 inches. It's not currently increasing by 10 inches per minute. That's not a rate of change that we're given. We're just told that right now, for now, r is 10 initially. And that's 10 inches. And we want to figure out how fast is the radius changing, and that's going to be in inches per minute for this problem. We are also missing v. We are not required to find it. I know that because I don't have a v in my derivative that I have to plug into. If I want to find v, I'll go into the original function and plug in r. So if I want to do that quick, I can plug into this function here to figure out what v is. I'll plug into the original if I'm missing a variable. I could do 4/3 pi times my r is 10 inches getting cubed. And I'm not going to multiply with the pi in there. It's going to make it a crazy decimal, but I am going to figure out what is 10 inches cubed times 4/3. And that gives me 4,000 thirds pi cubic inches. We really don't even need to know that, but if you wanted to find it, you'd plug into the original. All I did was 10 cubed times 4/3 pi gives me 4,000 pi inches cubed for that volume that we weren't given, that we don't actually need. Now I'm going to jump into the derivative and actually figure out the answer to this problem. How fast is the radius changing? So going into my derivative down there, I want to replace in these letters from the letters that were given up here. So we know dv dt is 15, so I'm going to replace that with the 15 from above. So we plug that in. Then we have 4 pi, and then we need to take r from above, which was 10, and plug it in. That was 10 inches getting squared, so we plugged in r. And we're trying to find dr dt, so naturally we don't have a number to plug in for that one. But I can do 10 squared and multiply that by 4 pi. So when I do that, I might bring it up here. I get 15 on the left still. And on the right, 10 squared is 100 times 4 is going to make it 400 pi. And that's going to be times dr dt. So lastly, to get dr dt on one side by itself, right now it's multiplied by 400 pi, so I'm going to divide both sides by 400 pi. And I could leave it just like that to get the exact answer. Dr dt is 15 divided by 400 pi. You could also look at what the decimal is to figure out if that makes sense, why the volume is increasing by 15 inches. And that is because the radius is increasing by 15 over 400 pi. And sometimes it makes more sense to look at the actual number, but you don't have to. You can leave it in that exact form. We would want to write our sentence though. We would say, as the volume increases by 15 inches cubic inches per minute, the radius increases because we got a positive derivative. We got positive 15 over 400 pi. The radius increases by 15 over 400 pi, and then we use the correct units for that one. That one's in inches per minute, and I can tell that this is inches per minute by referring back to my setup. Helps me figure out the correct unit. dr, r is in inches, dt, t for this one is in minutes. Increasing by 15 over 400 pi inches per minute, or make it a decimal if you want to see what that number looks like.